Inside these cleanroom suits is the hardware that powers the modern digital world. This single machine costs approximately $200 million and is arguably the most complex piece of equipment human beings have ever built. Its task is to print billions of transistors onto silicon wafers with extreme precision. The smallest features it carves are roughly 10 nanometers wide, a distance of about 45 individual atoms. At this scale, standard wavelengths of light are too large to be useful. It's like trying to trace a microscopic grid with a thick marker. The light is simply too blunt to resolve the fine details. Engineers overcame this by generating an entirely unnatural form of light that functions as an ultra-fine pen. The global digital economy now depends on our ability to trick the universe into letting us manufacture structures smaller than a biological virus. Creating that pen requires generating extreme ultraviolet light, or EUV. This process takes place deep underground in a pressurized vacuum chamber where conditions are forced to an extreme state. The entire process begins with a single, microscopic droplet of liquid tin falling freely inside the dark vacuum chamber. A specialized laser pulse hits the droplet, not to vaporize it yet, but to flatten the sphere into a wide pancake shape. A second laser, packing steel cutting power, then strikes the flattened tin. The metal vaporizes instantly, transforming into a violently glowing cloud of plasma. Inside that plasma, electrons are forced into higher orbitals. As they fall back down, they emit the 13 nanometer EUV light required for the printing process. This dual laser vaporization of falling metal happens exactly 50,000 times every second. We are literally vaporizing metal tens of thousands of times a second just to create the ink that powers our technology. EUV light is incredibly fragile. It is instantly absorbed by oxygen and even standard glass lenses, making it extremely difficult to control. To guide the light, the machine uses Bragg reflectors, mirrors built from dozens of alternating atomic layers of silicon and molybdenum. These mirrors bounce and focus the fragile light downward, successfully carving a microscopic maze into the final silicon wafer. This process allows for the fabrication of 2 nanometer architecture, creating chips with density that was recently considered impossible. To manage the heat generated by this density, engineers vary power lines underneath the data pathways, separating the electricity from the signals. This vertical stacking is like building a multi-level skyscraper in a dense city to maximize every available nanometer. Modern fabrication treats the microchip as a fully realized 3D metropolis, constructed entirely at the atomic scale. Even with $200 million of atomic precision, manufacturing eventually hits a limit where the universe itself refuses to cooperate. At the 2 nanometer scale, we encounter a physical hurdle called quantum tunneling. The transistor walls are now so thin that electrons simply teleport through them. They phase directly through solid matter, causing unpredictable power leaks. Engineering these chips is now a direct war against the fundamental laws of quantum mechanics. Because of these quantum leaks and stray dust, chips coming off the line are rarely born perfect. This leads to the silicon lottery, where manufacturers sort chips based on their microscopic flaws, a process known as binning. This means that a top-tier graphics card and its cheaper consumer counterpart are often cut from the exact same piece of silicon. The cheaper product is often just a failed premium chip, where the defective sectors have been permanently lopped away to ensure the rest of the circuit can still function. As we approach the 1 nanometer limit, atoms themselves will become too large to build with. Innovation is rapidly approaching an unbreakable wall of physics, leaving us to wonder what happens when we finally run out of space.